Mars pulls on everything at its surface with 3.711 meters per second squared. That is only 38% of Earth's gravity. A child conceived and born there would grow inside that weaker pull from the very first cell. And that child might never be able to come home safely. No human embryo has ever developed anywhere but Earth. So consider 3 facts we do have. Scott Kelly spent 340 days in orbit, and an artery in his neck widened by up to 15% in months. Astronauts can lose over 1% of their bone density every month without gravity's resistance, and the inner ear tunes its sense of balance to the gravity it first meets before birth. Everything we know comes from grown adults who left Earth and returned. We have no data on a body built from conception in weaker gravity. That gap is the whole problem. This episode follows the real evidence toward it. Bone models that predict severe loss on long missions. Radiation measured on the Martian surface by a real rover. A strange orbital experiment where jellyfish grew up with damaged gravity sensors, and the ethical fight over whether such a child should be born at all. If slow journeys through real space science help you rest, subscribe to Gravity of Sleep. Then we begin where the evidence begins. 2 identical twins, one in orbit, one on the ground. Scott Kelly and his brother Mark are identical twins. Their genetic codes match, cell for cell. Both men trained and flew as astronauts. That made them an experiment no laboratory could ever build on purpose. When Scott launched for his long stay in orbit, Mark stayed home. 1 twin in weightlessness, 1 twin under normal gravity. 2 nearly identical bodies, separated by a single force. Experiments like this almost never happen. You cannot ethically raise 1 twin in space and keep the other on the ground for comparison. Circumstance did it for us just once, with the Kelly brothers. That is why researchers studied them so intensely. A single year, 2 matched bodies, and a rare clean look at what leaving gravity does to a person. Scott spent 340 days aboard the International Space Station across 2015 and 2016. Through that whole year, researchers followed both brothers closely. They studied blood and vision and bacteria and the quiet activity of thousands of genes. The logic was simple. Whatever changed in Scott, but not in Mark, could be traced to spaceflight itself. The changes were real, and they were physical. The wall of the carotid artery in Scott's neck grew thicker during the mission. That vessel carries blood upward to the brain. Its diameter widened by roughly 9 to 15%. Mark's artery on the ground did nothing of the kind. In orbit, a healthy body was quietly rebuilding its own plumbing. Think about what that means. An artery is not a mood or a passing number. It is living tissue, reshaped by the conditions around it. Change the gravity, and the vessel itself changes. If a grown man's arteries respond that quickly, one question becomes hard to avoid. What would happen inside a body that is still being built? Then there were the genes. Weightlessness did not rewrite Scott's DNA, but it changed how thousands of his genes behaved. Some switched on, others quieted down. After he came home, most of that activity drifted back toward normal. About 91.3% of the changes returned to his pre-flight baseline within 6 months. Yet a small fraction never fully reset. Part of the imprint stayed. Something else stayed with him too. After landing, Scott's thinking was slower. His speed and accuracy on cognitive tests fell, and remained lower for 6 months after his return. His body had spent a year learning to live without gravity. Relearning Earth took far longer than anyone might guess. There is a comfort people reach for in these numbers. Most of what changed in Scott Kelly reversed. The arteries, the genes, the balance, nearly all of it tends to return once an astronaut is home. But reversal assumes there is a home to return to. It assumes a body that was once normal under Earth gravity, and can find that state again. A Mars-born child breaks that assumption completely. There would be no earlier Earth-normal version of that body waiting underneath. Hold that timeline in your mind. 1 year away produced artery changes, gene changes, and months of mental fog on the way back. And Scott Kelly was a healthy, fully grown adult. He carried decades of Earth gravity inside every bone before he ever launched. A child born on Mars would begin with none of that foundation. This is the difference that changes everything. Gravity is not an event, it is a constant condition. On Earth it presses on you without pause, from conception until death. Your bones grew dense because they were asked to carry weight. Your heart grew strong because it had to pump blood upward against a steady pull. Every tissue you have was shaped by a force you never chose and never notice. Now remove most of that force, not for a mission, not for a single year, remove it for an entire life, beginning before birth. That is the world a Mars-born child would inherit. And it points to a distinction we have to hold carefully. There is a difference between adaptation and development. Adaptation is what a finished body does when its conditions change. Development is how that body is built in the first place. A returning astronaut adapts. A Mars-born child would develop. We have studied adaptation for decades. We have never once observed development beyond Earth. The bone loss deserves a closer look, because it may be the sharpest edge of this problem. On Earth, bone is not a fixed scaffold. It is a living material, constantly torn down and rebuilt. Weight and strain tell the body how much bone to keep. Take the weight away, and the body stops maintaining what it no longer seems to need. In orbit, astronauts can lose more than 1% of bone density each month, sometimes as much as 1.5%. A child growing on Mars would never build to Earth's standard in the first place. Return for a moment to the inner ear. Deep inside it sit tiny organs that sense gravity directly. They are called the utricle and the saccule. They hold small crystals that shift with every tilt and pull, and they tell the brain which way is down. These organs form early in life, and they calibrate themselves to whatever gravity surrounds them. On Earth, that setting is 1 full gravity. In a Martian womb, the setting would be 38%. A brain tuned that way might read Earth itself as wrong. Consider one more thing that happens to bodies in orbit. Astronauts grow taller. Without gravity to compress the spine, the soft discs between the vertebrae expand, and the muscles along the spine relax. A person can gain up to 3% in height. For someone about 6 feet tall, that is close to 2 inches, or 5 centimeters, the effect is temporary. Within months of returning to Earth, gravity presses them back down, but it shows how quickly the human frame answers to the force around it. Now imagine a spine that grew its entire length under Martian gravity. This is why the twin study matters so much, and why it still cannot answer the real question. It proves that gravity, or its absence, reaches deep into the body. It touches arteries, it touches genes, it touches the brain. But Scott Kelly always had somewhere to return to. His bones remembered Earth. His balance remembered Earth. A child who never lived under Earth gravity would have no such memory. For that child, the baseline itself would be Mars. It is worth being honest about the shape of this evidence. Almost none of it comes from Mars. It comes from low orbit, from short missions, from animals, and from careful models. We are assembling a portrait of a Martian childhood out of fragments gathered a few hundred miles above Earth. The fragments are real, the measurements are real, but the child they describe is still entirely theoretical. Holding both of those truths at once is the only honest way to walk through this. For now, adult astronauts are the only window we have. Their bodies are the closest thing to a Mars experiment that history and ethics will allow. So we read them with care. We treat every artery, every gene, every lost gram of bone as a clue. And we keep returning to the gap between an adult who left Earth and a child who was born far from it. There is one more reason this question refuses to go away. It has already lived in our imagination. In 2017, a film called The Space Between Us pictured exactly this scenario. Its hero, Gardner Elliott, is the first human born on Mars. He grows up in Martian gravity, and he is told that his heart and his bones are not built for Earth. The film is fiction. The fear beneath it is not. Scientists have asked the same question, using measurements instead of a screenplay. And notice where the danger really sits. We tend to imagine the hazard as living on Mars. The greater hazard may be leaving it. A body tuned to 38% gravity would meet more than double that pull the instant it reached Earth. Bones that never carried full weight, a heart that never fought full gravity, a sense of balance set to another world entirely. For such a person, the trip home could be the most dangerous journey of their life. So we begin where the evidence begins. Not with a colony, not with a nursery beneath a dome. We begin with two brothers, 1 year, and a single difference between them. From there, the story moves outward, toward bone models that predict a slow structural collapse, toward radiation maps drawn by a rover on the Martian ground, toward a tank of jellyfish that grew up never knowing which way was down. Each step carries us closer to a child who does not yet exist, and to a question that no one, for now, can answer. Scott Kelly and Mark Kelly are identical twins. They share the same genome, letter for letter. For most of their lives, they shared the same world as well. Then, for 1 year, they did not. Scott Kelly spent 340 days aboard the International Space Station. His mission ran across 2015 and 2016. His brother Mark stayed on the ground the entire time. Two men built from one blueprint, separated by orbit. It was the closest thing science has ever had to a controlled experiment on the human body in space. One twin flew. One twin waited. Every difference that appeared between them carried meaning. The differences appeared. Scott's cardiovascular system did not stay the same. The walls of his carotid arteries thickened during the flight. These are the large vessels in the neck that carry blood to the brain. The diameter of those arteries increased by 9 to 15% while he was in orbit. Mark on Earth showed no such change. The body was quietly remodeling itself to a place without weight. A vessel that widens is not a small thing. It hints that the whole system for moving blood was being rebuilt for new conditions. And blood behaves strangely without gravity. On Earth, gravity pulls fluid toward the feet. The heart works against that pull all day, every day. In orbit, the pull is gone. Fluid drifts upward, toward the chest and the head. The heart no longer has to fight the same battle. So it adapts, as muscles and vessels always do, to the demand placed on them. The lesson is simple and unsettling. The human body does not hold a fixed shape. It is tuned constantly to the force it lives inside. Change the force, and the body follows. That is the thread that runs through everything ahead. Scott Kelly's genes told the same story at a finer scale. Spaceflight changed how thousands of his genes switched on and off. Most of that change was temporary. About 91.3% of the altered gene activity returned to his pre-flight baseline within 6 months of landing. The body knew how to come home. But a small fraction did not reset. Some changes persisted well past the 6-month mark. His system carried a faint signature of the year he spent away. There was another finding, and it is the one that lingers. After Scott returned to Earth, his thinking slowed. His cognitive speed and his accuracy both dropped compared to before the mission. This was not a fleeting fog of a hard landing day. The decline held for 6 months after he was back on the ground. The brain, like the bones and the heart, had adjusted to a place without weight. Bringing it back to full gravity was not instant. It was a recovery, measured in seasons rather than days. Now hold that result in your mind and change one thing. Scott Kelly was an adult. His body was fully built before he ever left the ground. He spent under a year in space, and when he came home, the price of that single year was still being paid half a year later. He had a baseline to return to. He had a childhood of Earth gravity written into every bone. A child born on Mars would have none of that. There would be no earlier version of the body to recover toward. The Martian body would be the only body that child had ever owned. This is why the twins study matters so much to a question about Mars. It is our clearest measurement of what leaving Earth does to a grown human, and it already shows the arteries changing, the genes shifting, the mind slowing. All of that from 340 days. All of that reversible, mostly because there was a home body to return to. The Martian child inverts the entire experiment. For that child, 38% gravity is not the deviation, it is the baseline. Earth would be the foreign world, so follow the evidence down into the skeleton, where the numbers grow starker. Bone is not a fixed scaffold laid down once and left alone. It is living tissue, torn down and rebuilt throughout life. Gravity is one of its main instructions. Weight bearing tells the bone how strong to be. Remove the weight, and the instruction fades. The body reads the low load as a signal that less bone is needed, so it stops maintaining what it no longer seems to use. In orbit, this shows up fast. Astronauts can lose roughly 1 to 1.5% of bone mineral density every month. That loss concentrates in the weight-bearing bones, the hip and the lower spine. These are exactly the bones that hold a standing body up against gravity. 1% a month may sound small. It is not. It compounds, month after month, in the places that can least afford to weaken. And this happens to trained adults who exercise in space specifically to fight it. Researchers have tried to project that loss across a real journey to Mars. In 2020, a predictive model did exactly this. It modeled the bone density in the femoral neck, the narrow part of the thigh bone near the hip. This is one of the most fracture-prone sites in the human body. The model ran 2 kinds of Mars mission. The shorter kind is called opposition class, lasting 400 to 600 days. The longer kind is called conjunction class, lasting 1,000 to 1,200 days. The shorter mission was already severe. It predicted a loss of 15.6 to 22% of femoral neck bone density. The longer mission was worse. It predicted a loss of 32.4 to 36.8%. Read those numbers slowly. 1/3 of the bone at the hip, gone. In the model, every astronaut on the long conjunction class mission developed osteopenia, the thinning of bone that precedes true fragility. That is 100% of the crew. And about 33% crossed into the range of osteoporosis risk, where fractures come easily. Remember, these projections describe adults who arrived with a full Earth-built skeleton and merely lost part of it over a mission. They still walk in low gravity the whole time. Their bones do not need to be strong on Mars, where a body weighs so little. The danger was never really the weakness on Mars. The danger was the return. A hip that lost 1/3 of its density in space would meet full Earth gravity again on landing, and a bone that thin can break under an ordinary load. The same erosion runs through muscle, and it moves even faster than bone. Muscle responds almost immediately to disuse. In microgravity, the great postural muscles of the legs and back have almost nothing to push against, so they shrink. Astronauts can lose up to 20% of their skeletal muscle mass in missions as short as 5 to 11 days. On longer flights, that loss can reach 30%. A body wastes what it does not use, and gravity is what it normally uses those muscles to resist. Exercise fights this, but it does not win outright. Astronauts on the space station train hard against the loss. Even so, 10 to 20% muscle loss is typical over a long stay. The calf muscles tell the story clearly. Over 6 months, calf muscle loss ranged from about 7% in those who exercised the most, up to 17% in those who exercised the least. Effort narrows the damage. It does not erase it. The muscle still fades, because the force that built it is gone. Now imagine a body that never had that force to begin with. A child raised in 38% gravity would build muscle for a world where everything weighs a little over 1/3 of its Earth value. The legs would be strong enough for Mars. Walking, standing, lifting, all of it calibrated to a gentle pull. That same body, set down on Earth, would suddenly weigh more than twice as much. Muscles tuned to a light world would be asked to carry a heavy one. There would be no earlier, stronger version of those muscles waiting underneath. Mars would be all they had ever known. This is the shape of the whole problem, seen from the inside of the body. Bone tuned to light gravity. Muscle tuned to light gravity. A heart and a set of arteries tuned to light gravity. Each system, on its own, adapts sensibly to the world it lives in. That is exactly what makes the return so dangerous. The adaptation is not a flaw. It is the body doing precisely what it evolved to do. It fits itself to its home. The trouble begins only when you try to move it to a different home, one it was never built for. And there is a final piece to this, one that the astronauts feel the moment they land. Their bodies have spent months rebuilding for a world without weight. Then, in a matter of hours, they are handed full gravity again. The heart that stopped fighting the downward pull of blood must suddenly fight it once more. And for many of them, on the first day back, that fight does not go well. Consider what actually happens on that first day back. When a returning astronaut stands, blood drains toward the legs. The heart must race to push it upward again. On Earth, the body does this without a thought. After months without weight, the reflex has grown weak. Doctors call the result orthostatic intolerance. It is the plain fact of a body that can no longer stand. The measurements here are blunt. Nearly 30% of space shuttle astronauts who flew without anti-gravity suits could not hold their blood pressure upright on landing day. Those were short flights. The effect only deepens with time. After stays of 4 to 5 months aboard the Mir station, the result was harsher. 5 of the 6 astronauts tested could not finish a simple standing test on the day they came home. They lay on a table that slowly tilted them toward vertical. They were asked to hold that upright position for 10 minutes. Most of them could not. Hold that fact against the premise. These were trained adults. They spent their whole lives under full gravity. Their hearts and vessels were built for 1 Earth of weight, and they lost that footing after only a few months away. Now imagine a heart that never knew full gravity at all. A child grown from conception in 38% of Earth's pull would have a cardiovascular system tuned to a fraction of the load. The reflex that failed the Mir cruise would have nothing to fall back on. It would be facing full Earth gravity for the first time in its life. The muscles tell the same story. In microgravity, the body sheds the very tissue that holds it upright. On missions as short as 5 to 11 days, astronauts can lose up to 20% of their skeletal muscle mass. On longer flights, the loss can reach 30%. The muscles that suffer most are the ones that fight gravity every day. The calves, the thighs, the muscles that run along the spine. They waste because there is suddenly nothing to push against. The space stations fight this loss with exercise, and the fight is real work. Crews train for hours. Even so, 10 to 20% muscle loss is common over a long stay. The exact figure tracks with effort. Over 6 months, calf muscle loss ranged from about 7% in astronauts who trained hard to 17% in those who trained less. The lesson is quiet but clear. Gravity is not optional maintenance for the body. It is the load the body is built around. A Mars child would face a version of this that has no name yet, because no one has lived it. An adult astronaut loses muscle they already built on Earth. They have something to lose. A child raised in low gravity might never build that reserve in the first place. Their muscles would grow only as strong as their world demanded, and their world would demand very little. Then, there is the strangest change of all, and it points straight at the shape of the body. In space, astronauts grow taller. Without gravity to compress the spine, the soft discs between the vertebrae swell with fluid. The muscles that normally clench the spine into a column relax. The spine unfolds. Astronauts can gain up to 3% in height. For someone near 6 feet tall, that is roughly 2 inches, about 5 centimeters, added in orbit. The effect is temporary for them. Within months of returning, gravity presses the spine back down, and the extra height disappears. But notice why it happens. The adult skeleton was already finished, already set in its final proportions, before it ever left the ground. Space only stretched what was already built. A child is not finished. A child is being assembled. Bone is laid down, reshaped, and hardened across years of growth, and it takes its cues from the forces acting on it. A skeleton that grows under a third of Earth's gravity would not simply be a lighter version of an Earth skeleton. It might be a different skeleton. Longer, thinner, laid down for a world where standing costs almost nothing. We do not know this for certain. No human skeleton has ever grown anywhere but here. But everything we understand about how bone responds to load points in the same uneasy direction. This is the heart of why the return is the true measurement. Everything discussed so far, the bone, the muscle, the vessels, the spine, describes a body adapting downward to gentleness. The danger is not the adaptation, the danger is reversing it. To leave Mars for Earth is to take a body optimized for lightness and drop it into a gravity nearly 3 times stronger. The Mir crews needed help to stand after a few months. A Mars-born traveler would arrive with a lifetime of that lightness written into every tissue. And there is a system we have not yet examined, one that may matter more than bone or muscle, because it decides which way is down. It is the sense of balance. Deep inside the inner ear sit 2 small organs, the utricle and the saccule. Together they are called the otolith organs. They hold tiny crystals that shift with movement and with gravity. When the crystals settle, they tell the brain where down is. This is the vestibular system, the body's private compass for the pull of a planet. Here is the part that matters for a child. This system develops early in life, well before birth, and it does not develop in a vacuum. It calibrates itself to the gravity it can feel. The developing body reads the constant downward vector around it and tunes its sense of balance to match. On Earth, that vector is one full gravity, and every human who has ever lived has been calibrated to it in the womb. A fetus developing on Mars would calibrate to something else. Its otolith organs would settle against 38% of Earth's pull, and that fraction would become the definition of down. The compass would be built for Mars, not adjusted for Mars, built for it from the beginning as the only gravity it had ever measured. We cannot test this on a human, but we have watched a simpler creature grow up without knowing which way was down, and the result is one of the more haunting experiments in spaceflight biology. In 1991, a shuttle mission carried moon jellyfish into orbit. The choice of animal was deliberate. Jellyfish sense gravity using small structures built from calcium crystals, structures that work on the same basic principle as the crystals in the human inner ear. If gravity shapes a balance organ, the jellyfish would show it plainly. The scale of the experiment was remarkable. The mission launched with 2,478 jellyfish in an early polyp stage. Over 9 days in weightlessness, they multiplied and matured into nearly 60,000 young jellyfish. An entire generation came into being, having never once felt the pull of a planet. Their gravity-sensing organs formed in orbit, tuned to nothing. Then, they were brought home and watched. The jellyfish that had developed in space did not swim like the others. Their pulsing was off. Their movement was disordered. In the space-raised animals, abnormal swimming and pulsing appeared in about 18.3% of individuals. Among jellyfish raised on the ground, the same abnormality appeared in only 2.9%. The organ that tells a body how to move through its world had not formed correctly, because the world it formed in had no down to teach it. A jellyfish is not a child. The distance between the two is vast, and honesty requires saying so plainly. But the experiment isolates the exact fear. When a gravity-sensing organ develops in the wrong gravity, it develops wrong. The structure comes out miscalibrated for any world with weight. For the jellyfish, the wrong world was Earth. For a Mars-born child, the wrong world would be the very planet its parents came from. Picture that arrival then. A young person who has never fallen the way we fall, whose sense of balance was tuned to a lighter pull. Standing on Earth for the first time, that inner compass would suddenly disagree with everything the eyes report and everything the ground insists. The dizziness that grounds returning astronauts for days is a temporary correction in a system that was calibrated here first. In a body calibrated on Mars, there would be no earlier setting to return to, so the picture keeps deepening in the same direction. The bone would be lighter, the muscle would be thinner, the heart would be tuned to a gentler climb. The spine might be longer, and the sense of balance itself might be set to a planet that Earth would constantly contradict. Each of these is drawn from real bodies and real experiments, adults returning from orbit and animals grown in weightlessness. None of it is drawn from a child, because no child has ever been the test. That is the missing measurement at the center of the whole question, and yet all of it still assumes the simplest thing has already happened. It assumes the child was carried and born at all. That assumption hides its own set of unknowns, and they may be the deepest ones of all. Before we can ask whether a Mars-born body could ever come home, we have to ask an earlier question: whether that body could safely begin. Consider the very first step. It happens long before anyone counts the weeks of a pregnancy. It is conception, and even here the ground grows uncertain. On Earth, this process assumes a steady downward pull. Cells move, orient and divide inside that constant field. In weightlessness, that field is gone, and the machinery behaves strangely. Studies in microgravity and in simulated microgravity point to a specific problem. Sperm lose their sense of direction. Their motility falters. Their swimming turns disoriented, as if the usual cues have been scrambled. Researchers also report hormonal disruption in these reproductive studies. These are not small footnotes. They touch the earliest moment of a new life. Then there is the radiation, and it does not spare the cells that make a child. In animal models, radiation exposure is linked to increased damage in sperm donor. The genetic material carried into a new embryo can be broken before that embryo exists. The same environment appears to accelerate the loss of ovarian follicles. Those follicles are the finite reserve of eggs a body is born with. A Mars child would be conceived inside a radiation field that adults already struggle to survive. We do not know what that field does to the first cell of a new person. We only know it is not gentle. Suppose conception succeeds anyway. Suppose an embryo forms and begins to grow. Now the pregnancy itself must proceed in a world it was never built for. Here the clearest evidence comes not from humans, but from animals carried into orbit. Pregnant rodents have been flown in space and studied in simulated microgravity on the ground. The results are consistent, and they lean in one direction. Fetal weight develops more slowly. Skeletal development is delayed. The placenta, the organ that feeds the growing body, develops more slowly as well. When birth comes, labor is prolonged, and in the first week after birth, more of the newborns die than in the Earth-based controls. Every part of that finding matters. The placenta is the lifeline. A slower placenta is a thinner thread. Delayed skeletal growth means the frame of the body is already behind. A prolonged labor is a more dangerous labor, for mother and child alike, and higher mortality in the first days is the plainest signal of all. This is what altered gravity does to creatures that reproduce quickly and can be studied in numbers. It is not proof of what would happen to a human. It is a warning written in a smaller hand. Notice what all of this shares. None of it comes from a human pregnancy. No human has ever been conceived, carried, or born anywhere beyond this planet. There is no direct data on how a person develops off Earth. There is only extrapolation, drawn from animals, from cells, and from the physics of a field that will not be there. So the earliest questions turn out to be the hardest. Not whether a grown Martian could return to Earth, but whether a Martian could begin at all. The first cell might be damaged. The pregnancy might falter. The developing body might build its most delicate instruments to the wrong specification. Each stage carries its own silence where an answer should be. This is the point where the science presses against something larger than biology. If a colony ever attempted this, the first child would not be a patient with a known condition. That child would be the first of a kind. Every measurement taken would be a measurement never taken before. Every risk accepted would be accepted on the child's behalf, by adults who could not know the outcome. The medical uncertainty becomes an ethical weight, and that weight has already drawn serious attention, long before any such child exists. Bioethicists have taken the premise seriously. The most detailed work in this area comes from a philosopher named Konrad Socek, writing with colleagues from around 2018 onward. Their analyses do not read like science fiction. They read like a list of decisions no one has ever had to make. What is the value of a human life deliberately created in a place that is trying to kill it? Who decides whether a pregnancy on Mars should continue? There would be no hospital to return to. There would be no ship leaving soon. What happens to the ordinary rules around abortion when a settlement is cut off from Earth for months at a time? These are not abstractions. They are the practical questions of a place where every birth is also an experiment. Socek and his colleagues raise a further possibility, and it is a heavy one. They ask whether it might one day be considered justified to engineer children specifically to survive on Mars. A body altered before birth to hold its bone, to resist radiation, to tolerate a gravity that would otherwise reshape it. The idea is not offered as a plan. It is offered as a warning about where the pressure leads. If ordinary human development cannot safely happen on Mars, then the temptation to redesign the human becomes real, and the first children would carry those choices in their cells without ever having agreed to them. That is the phrase that keeps returning in this literature. A Mars-born child would effectively be the subject of an experiment, not a metaphor for one. An actual subject, in the plainest sense, brought into a controlled and dangerous environment to see what happens to a human body that starts there. On Earth, we long ago agreed that people cannot be enrolled in experiments without consent. A newborn cannot consent to anything, and a child conceived on Mars would be enrolled in the most consequential experiment imaginable, simply by being born. All of this assumes something that is itself far from settled. It assumes there is a colony large enough for the question to arise at all. A single crew of explorers is not a population. For a Mars settlement to sustain itself, to reproduce across generations without constant rescue from Earth, it would need a certain minimum number of people. The published estimates vary widely, which tells you how uncertain the ground still is. One study appeared in 2020 in the journal Scientific Reports. Its author, the researcher Jean-Marc Salotti, calculated a minimum viable number of about 110 people. A more recent simulation went further. It modelled not only resources, but the mix of personalities that could hold a community together. That study suggested the number might fall as low as 22, assuming a resupply from Earth every 2 years. The gap between 22 and 110 is not a rounding error. It is a measure of how little we truly know about keeping humans alive together, so far from home, for so long. And notice what both numbers quietly require. They require that people do not merely survive on Mars. They require that people are born there. A colony that cannot reproduce is not a colony. It is a mission with an expiration date. So the question of the first Mars child is not a curiosity at the edge of the story. It sits at the very center of whether a permanent human presence on Mars is even possible. Which returns us to the child who does not yet exist, and to the body that child would build. Assume, for a moment, the hardest steps all succeeded. Conception held, the pregnancy reached its end. A living child was born beneath a pink Martian sky. That child would still inherit every earlier concern in this story, now stacked on top of one another. The lighter bone, the thinner muscle, the heart tuned to a gentler pull, and the balance system, calibrated from before birth to a world that Earth would forever contradict. The question was never only whether such a child could be made. It is what world that child would then belong to, and whether any other world would ever accept them. Consider the balance system more closely. It is older than almost every other sense. Deep inside each ear sit two tiny organs. They are called the utricle and the saccule. Together they form what scientists call the otolith organs. Inside them rest small crystals of calcium carbonate. Gravity pulls on those crystals constantly. The pull bends tiny hair cells beneath them. Those bent cells tell the brain which way is down. This is how a body knows it is upright. This is how its senses tilt and rise and fall. Here is the unsettling part. This system begins forming early in fetal life. It calibrates itself to whatever gravity surrounds it. On Earth, that reference is one full gravity. Every human who has ever lived was tuned to that value. The crystals, the hair cells, the neural map, all of it assumes the same downward pull. A child developing on Mars would calibrate to something else. Its inner ear would learn a world at roughly 38% of Earth's gravity. The reference written into its balance would be Martian, not terrestrial. We cannot test this on a human. No one would allow it, and no one should. But there is one experiment that hints at the danger. It did not use humans. It used jellyfish. In 1991, a space shuttle carried an unusual payload into orbit. The flight was a dedicated life sciences mission. Aboard it were 2,478 moon jellyfish polyps. A polyp is the small, anchored early stage of a jellyfish. In just 9 days of weightlessness, they multiplied. Nearly 60,000 young jellyfish developed in space. Scientists call these young forms ephyrae. The reason jellyfish matter here is precise. They sense gravity using crystals, much as we do. A jellyfish carries structures called graviceptors. Inside them sit calcium-based crystals. Those crystals settle under gravity and tell the animal which way is up. The design is different from a human ear, but the principle is startlingly similar. Both rely on a heavy crystal falling in a known direction. So the jellyfish became a test of gravity-blind development. What happens when a gravity-sensing organ forms without gravity to guide it? The answer arrived when the animals were studied. The ephira that developed in space showed abnormal pulsing and swimming. Their graviceptors had not formed correctly. 18.3% of the space-grown jellyfish showed these movement problems. Among jellyfish raised on Earth, the figure was 2.9%. The gap is not subtle. Developing without normal gravity left a lasting mark on the organ that senses it. A jellyfish is not a child. The comparison must be handled with care. But the lesson is hard to dismiss. A gravity-sensing organ, built during development in the wrong gravity, may build itself wrong. It does not simply adjust later. It forms around the conditions present while it grows. This is why the Mars child returns, again and again, to a single problem. Not whether the body can be kept alive, whether the body forms correctly in the first place. And that uncertainty reaches back further than birth. It reaches into the pregnancy itself. Here the evidence thins, but it is not empty. We have flown pregnant animals, mostly rodents, some in orbit, some in machines that simulate weightlessness on the ground. The results are quiet warnings. Pregnant rodents exposed to these conditions tend to produce smaller fetuses. Fetal weight lags behind Earth-based controls. Skeletal development is delayed. The placenta, the organ that feeds the developing young, also develops more slowly. Labor itself can run longer than normal, and in the first week after birth, more of the newborns die. None of this proves a human pregnancy would fail. Rodents are not people, and simulated gravity is not Mars. But every arrow points the same direction. Development under altered gravity is development under stress. The stress may begin even before conception. Reproduction depends on cells that are themselves sensitive to their surroundings. In microgravity studies, sperm behave strangely. Their motion changes. Instead of swimming in clean, directed paths, they become disoriented. They struggle to orient and move as they would on Earth. Hormonal signals that guide reproduction can be disrupted as well. Radiation adds a second insult. We will return to radiation in detail, because it shapes the whole Martian story. For now, note only its reproductive edge. In animal studies, radiation exposure is linked to increased damage in sperm DNA. It is also linked to faster loss of a female's ovarian follicles. Those follicles are the finite store from which eggs are drawn. Damage them, and the window for reproduction narrows. Put these pieces together, and the picture sharpens. Conception may be harder, the pregnancy may be harder, the development may be harder, and the child, if born, inherits a body assembled under conditions no human body has ever known. Each stage carries its own uncertainty. Stacked together, they define why scientists speak so cautiously about the first Mars birth. There is a further weight to all of this, and it is not medical, it is moral. Suppose a colony one day decides to try. Suppose a woman there becomes pregnant, whether by plan or by chance. The child that results cannot consent to any of it. It cannot agree to be born into low gravity. It cannot agree to carry a body tuned to a world it may never leave. It becomes, in the plainest terms, the subject of an experiment it never chose. This is not a rhetorical flourish. It is the argument raised by bioethicists who study the question. One of them, Konrad Sotik, has written repeatedly about human reproduction on Mars. His analyses do not offer easy answers. They raise hard ones. What is the value of a human life created deliberately in a hostile place? What happens to abortion policy in an isolated settlement, far from Earth's laws and Earth's medicine? And if survival on Mars required altering the child's biology in advance, through genetic engineering, would that ever be justified? Sotik and his colleagues state the discomfort directly. A Mars-born child would effectively be the subject of an experiment. That single sentence carries the whole ethical burden of this story, and yet the settlements are still being planned. The scenarios that make a Mars child likely are not fantasies drawn from film. They come from serious estimates of how many people a lasting colony would need. Those numbers vary widely, but they all describe a community large enough that, sooner or later, someone would be born there. Which means the ethical question cannot be postponed forever. If people go to stay, children follow. The science and the conscience must both be ready before the first cry is heard beneath that pink sky. Consider first how large a settlement would have to become. That number decides whether a Mars birth stays rare or turns inevitable. In 2020, the researcher Jean-Marc Salotti published a study in the journal Scientific Reports. He tried to calculate the smallest colony that could sustain itself. His model weighed the labor each task demanded against the work each colonist could supply. The figure he reached was 110 people. Below that threshold, he argued, the settlement would slowly fail. The colonists would spend more effort surviving than they could ever produce. 110 was the point where the community could hold its own. That estimate is not the only one on the table. A later study approached the same question from a different direction. It used an agent-based simulation, modeling colonists as individuals with distinct temperaments. It asked how personality and not only raw labor would shape survival. That model returned a much smaller number. As few as 22 people might endure, given the right mixture of character types. But the lower figure carried a strict condition. It assumed steady resupply from Earth, arriving roughly every 2 years. 22 settlers could last only while Earth kept sending help. The gap between those numbers is enormous. One study says 110, the other says 22. Both are serious attempts, and both remain estimates. Nobody has run the experiment, yet the disagreement hides a shared conclusion. Whether the founding number is large or small, it describes a community meant to stay. A resupplied outpost of 22 is still a group living lives on that surface. A self-sufficient town of 110 is a place raising a second generation. In either case, people are not merely visiting, they are settling. And where people settle, children eventually arrive. This is why the ethical question cannot wait for certainty. The planners are not asking whether a Mars child is possible in principle. They are estimating how many adults must go before one becomes likely. The moment a colony reaches that size, the abstract debate becomes a delivery room. The bioethicists writing today are trying to think ahead of that room. They want the argument settled before the first pregnancy begins, not during it. So return now to the body that pregnancy would produce. Set aside the ethics and look only at the physics. A child conceived and grown on Mars would develop inside 38% of Earth's gravity. Every stage of that growth would answer to a weaker pull. The skeleton would form under it, the heart would learn to move blood against it, the inner ear would calibrate its sense of balance to it. None of these systems would know that a stronger world existed. They would simply build themselves to fit the world they could feel. And here the central problem sharpens into a single measurement we cannot yet take. The measurement is the return trip. It is the moment a Mars-born body meets Earth's full gravity for the first time, from 0.38 g to 1 g. That change is the entire riddle folded into one number. For adults who trained their whole lives under Earth's pull, that homecoming is already brutal. Recall what adult astronauts endure on landing day. Roughly 30% of space shuttle astronauts who did not wear anti-gravity suits could not hold their blood pressure while standing upright when they came home. Their hearts, adapted to weightlessness, could no longer fight Earth's pull to keep blood in the brain. After longer stays, the effect grew worse. Following 4 to 5 month missions aboard the station Mir, 5 of 6 astronauts tested could not finish a 10-minute upright tilt table test on the day they landed. These were healthy, highly trained adults. Their bodies had spent only months away from Earth's gravity. They still nearly fainted the moment it returned. Now imagine a body that has never known Earth's pull at all. An adult astronaut is a native of Earth adjusting back. A Mars-born child would be a native of Mars arriving for the first time. The adult has a baseline to recover toward. The child would have no baseline on Earth to recover to. Everything the adult lost and slowly regained, the child would never have possessed. The fainting problem that troubles returning astronauts might, for such a child, be the ordinary condition of standing up on Earth. The skeleton deepens the concern. Adults in weightlessness can lose roughly 1 to 1.5% of bone mineral density each month in the weight-bearing hip and lower spine. The predictive models for long Mars missions run those losses into staggering territory. A conjunction-class mission of 1,000 to 1,200 days could cost 32 to nearly 37% of femoral neck density. In that modelling, every conjunction-class astronaut developed osteopenia, and a third reached the range of osteoporosis risk. But those figures describe adult bones losing what they already had. A Mars child's bones would never build toward Earth strength in the first place. They would be laid down for a world that asks little of them. Under 1 g, a skeleton tuned to 0.38 g would suddenly carry more than 3 times the load it was designed to bear. The muscles tell the same story from another angle. Microgravity can strip up to 20% of skeletal muscle in missions of only 5 to 11 days, and up to 30% on longer flights. Even with the station's demanding exercise routines, 10 to 20% muscle loss is typical, and calf muscle alone can shrink between 7 and 17% over half a year. A growing body in low gravity would build only the muscle its environment demanded. On Mars, that demand is small. The legs that carry a child easily across a Martian floor might buckle under the weight of the same child standing on Earth. Even height enters the question. Adults grow up to 3% taller in space as the spinal discs expand and the muscles along the spine relax without gravity to compress them. For a 6-foot person, that is about 2 inches, roughly 5 centimeters, and it reverses within months of coming home. In an adult, this is a temporary stretch that gravity soon undoes, but a spine that forms across an entire childhood under weak gravity is not stretching temporarily. It is developing into its final shape. What that shape becomes, and how it would answer to Earth's compression, is exactly the kind of thing no one has measured, because no one has ever grown up anywhere but here. Then there is the quietest system of all, the one that senses which way is down. The inner ear carries the otolith organs, the utricle and the saccule. They detect gravity and acceleration, and they take shape early in fetal life. They calibrate themselves to the gravitational vector the developing body actually feels. On Earth, that vector is 1g, straight down, constant from before birth. In a Martian womb, the vector would be weaker. The child's sense of balance would be tuned, from the very beginning, to a gentler pull. This is not a muscle that can be rebuilt with exercise. It is a reference frame set during development. Bring that child to Earth, and the ground itself might feel wrong in a way no training could easily correct. We are not left to guess entirely about developing gravity sensors, because one strange experiment offered a glimpse. In 1991, the shuttle mission carried 2,478 moon jellyfish polyps into orbit. Over 9 days of weightlessness, they multiplied into nearly 60,000 young jellyfish. Jellyfish sense gravity using tiny calcium-based crystals, structures that echo the mineral sensors inside the human inner ear. When the space-grown jellyfish were examined, 18.3% showed abnormal pulsing and swimming. Among jellyfish that developed on Earth, only 2.9% did. The creatures that grew up without a clear sense of down did not move normally. Their gravity organs, formed in the wrong environment, never worked quite right. A jellyfish is not a child. The comparison must stay honest, but the principle it demonstrates is precisely the one at stake. A gravity sensing system built in the wrong gravity can develop wrong. Multiply that principle across a whole human nervous system, a whole skeleton, a whole cardiovascular architecture, and the scale of the unknown comes into focus. We have watched a simple animal's balance organs fail to form correctly off Earth. We have no idea what a complex one would do. This is where the science, stated plainly, admits its own limits. The reference summaries on Mars-born children do not pretend to know the answer. They describe the whole question as unresolved. The possibility of adapting to Earth later in life ranges, in their own words, from a trivial problem at one end to an insurmountable obstacle at the other. That is not a small window. It is the entire space between easy and impossible, and the only thing that could narrow it is the one thing we do not have: real, long-term research on how a body develops across years of partial gravity. Until that research exists, the honest position is uncertainty. It is telling that fiction reached this idea before science could answer it. The 2017 film The Space Between Us imagined exactly this premise. Its central figure, Gardner Elliott, is the first human born on Mars. He grows up in Martian gravity, and he is told that his heart and his bone density are not built to withstand life on Earth. The film is a story, not evidence. Its physiology is dramatized, not measured. But the anxiety it dramatizes is real, and it is the same anxiety the researchers describe. A child of Mars, tuned to a lighter world, meeting the heavier world of its own species. The screen turned that fear into a character. The laboratories have turned it into an open file. Open that file, and the first page is not about a child. It is about arithmetic. Before anyone is born on Mars, a settlement has to exist. And a settlement is not one landing. It is a population large enough to feed itself and repair itself, large enough to hold a gene pool that does not slowly collapse. Researchers have tried to put a number on that threshold. In 2020, a study in Scientific Reports set the minimum at 110 people. That figure came from Jean-Marc Solotti, who modelled the labour a colony needs to survive. Growing food, making breathable air, fixing machines that were never meant to be fixed so far from any factory. Below 110, the model showed the colony spending more effort than it could ever produce. The settlement would fail slowly, and then all at once. Other researchers pushed the number down. A later agent-based simulation suggested a colony might hold with as few as 22 people, but that number arrived with conditions. It assumed the right mixture of personalities under constant pressure. It assumed resupply from Earth every 2 years. It assumed that the hardest part of a Mars colony is not the machines, but the minds living inside it. 22 or 110. The point underneath is the same. A Mars-born child is not the beginning of this story. It is a late chapter. It arrives only after a small human population has already chosen to stay and to grow in a place that was never built for growing anything. And here the science runs out of measurements and into questions it cannot yet ask a body to answer. We do not know whether a human pregnancy can even proceed normally in low gravity. No one has ever tested it. What exists instead is animal work, and the animal work is not reassuring. Pregnant rodents have been flown in space and raised in simulated low gravity. Their pregnancies did not unfold the way they do on Earth. Fetal weight came in low. Skeletal development lagged behind schedule. The placenta itself, the organ that feeds a growing fetus, developed more slowly. Labor ran longer than it should, and in the first week after birth, more of the newborns died than in the Earth-bound controls. Those are rodents, not people. The caution has to be stated plainly. A rat is not a human, and a short flight is not a Martian childhood. But the pattern is consistent enough to trouble the people who study it. Development is a sequence. Each stage rests on the one before it. Change the force acting on the body at the very start, and every later stage inherits that change. The concern is not that one system fails. It is that the whole schedule of growth was written for a heavier world. The trouble may begin even earlier than pregnancy. Before a fetus, there is conception, and conception has its own difficulties in space. Studies of reproductive cells in microgravity and in simulated microgravity describe sperm that swim without direction. Their motility drops. Their orientation is disturbed, as though they can no longer read which way to go. Hormonal signaling falters alongside them, and radiation adds a second injury. In animal models, radiation exposure increases the number of breaks in sperm DNA. It accelerates the loss of a female's ovarian follicles, the finite store of eggs a body is born with and can never replace. Each of these findings is an open risk factor, not a settled verdict, but together they describe an environment hostile to the very first cells of a new life, long before that life has any body of its own to protect it. Suppose all of that is somehow overcome. Suppose a pregnancy holds, and a child is born beneath a pale Martian sky. The questions do not stop there. They only change from biology into ethics. A group of bioethicists, led by Konrad Socek, has spent years writing about exactly this moment. Their conclusions are uncomfortable, and they are meant to be. A child born on Mars cannot consent to being born there. It cannot agree to a body shaped by low gravity and heavy radiation. It cannot choose to become, in their words, the subject of an experiment. And yet, that is precisely what it would be. The first Mars-born child would be the living test of a hypothesis no one has been allowed to run. Socek and his colleagues push further into places most people would rather not look. In an isolated colony, far from any hospital on Earth, what happens when a pregnancy goes wrong? What becomes the policy on ending a pregnancy when there is no way to save the mother? They ask whether it could ever be justified to engineer a child's genes in advance, to give it a better chance of surviving a world its unmodified body could not. These are not abstract puzzles for them. They are the practical decisions a colony would face the first time 2 settlers chose to have a child. The value of a single human life looks different when that life is asked to begin in a place actively working to end it. And beneath the ethics, the physical question keeps returning in a sharper form. Everything measured so far was measured on adults. Adults who grew up under Earth's full pull, who calibrated their bodies here, and only later carried them into space. Their bones were built at 1 full gravity before anything began to erode. Their inner ears learned which way was down in a nursery on this planet. When they returned, they were not learning gravity, they were remembering it. A Mars-born child would have nothing to remember. Its skeleton would be assembled under 38% of Earth's pull from the first cell division onward. Its balance organs, the tiny otolith structures called the utricle and the saccule, would settle their sense of down against a Martian vector and call it normal. There would be no earlier version of the body to fall back on. The child would not be adapting to Mars. Mars would be all it had ever known. That is the difference no proxy can fully capture. An adult adapts. A child is built. And a body built for one gravity does not obviously carry over to another. This is why the return trip, not the outbound trip, is the measurement that matters most and the one we cannot make. We have watched adults leave one gravity and struggle to re-enter it. We have never watched a body that began in low gravity attempt Earth for the first time. The direction of the harm may simply reverse. For an astronaut, the danger is coming home. For a Mars child, home would be the danger. Layer radiation on top of that growing body, and the numbers grow heavier still. Curiosity's radiation detector measured the Martian surface, delivering roughly 2/3 of a millisievert of radiation every single day. That figure sounds small until you multiply it by a childhood. The European Space Agency caps an entire astronaut career at 1 sievert, a limit tied to about a 5% rise in lifetime fatal cancer risk. NASA draws its own line at a 3% excess risk threshold. These are ceilings for trained adults, accepted knowingly, for a few years of work. 1,000 days on the Martian surface, under 3 Earth years of a child's life, would deliver roughly 2/3 of a sievert. A child does not stop at 1,000 days, it keeps living, and the dose keeps accumulating, quietly, through every year of growing up. The invisible ceiling that an astronaut is warned never to exceed would be crossed simply by surviving to adolescence. None of this decides the case. That is the honest and frustrating truth at the center of the file. We cannot say with certainty that a Mars-born child would be unable to visit Earth. We also cannot say that it could. Every piece of evidence is a proxy standing in for a measurement no one has taken. The bone models describe adults on mission timelines, not infants across a lifetime. The pregnancy studies are rodents. The reproductive findings are risk factors, not outcomes. The radiation totals are dosimeters bolted to a rover, not to a growing spine. Each fact is real, each one points the same uneasy direction. But not one of them was gathered from the body the question is actually about. So the file stays open, and it stays open for a reason. The only instrument that could close it does not exist. It would be a long-term study of a human body developing across years of partial gravity, from conception onward, watched the whole way. That study cannot be run in a laboratory, and it cannot be run ethically on a volunteer, because the volunteer would be a child who could not agree to any of it. The knowledge we want most is the knowledge we may be least willing to earn, and so we are left circling the edges of the answer, measuring adults, flying rodents, growing cells in orbit, and reading the results like weather forecasts for a storm that has not yet formed. There is one more direction the evidence points, and it is the quietest of all. Everything we have measured suggests that gravity is not a setting the body checks against once. It is a background the body assumes at every moment, and writes into its bones, its blood pressure, its sense of balance. A body assembled under a weaker pull would not be broken. It would be correct for Mars. It would be exactly what 38% of a gravity asks a growing human to become. The problem is only revealed the moment that body tries to leave, and whether it could ever make that crossing safely remains, for now, unmeasured and unknown. For a long time this stayed a thought experiment. It required no answer, because no one was staying. Every human who left Earth came back, or intended to. A Mars-born child only becomes possible when someone decides to remain. That decision is no longer hypothetical. Space agencies and private companies now speak openly of permanent settlement. They do not mean a visit, they mean a home. A home needs a certain number of people. In 2020, the researcher Jean-Marc Salotti published a calculation in the journal Scientific Reports. He asked how few settlers could sustain themselves on Mars without constant rescue from Earth. His answer was 110 people. Below that number, the colony cannot produce what it consumes. It cannot maintain its own machines and replace its own losses. 110 was the floor beneath which a settlement slowly fails. A later study reached a smaller and stranger number. Using a simulation of how people behave, researchers modeled personalities under extreme isolation. They found a colony might survive with as few as 22 people. That number assumed a resupply ship from Earth every 2 years. It also assumed the right mix of temperaments. Some personality types held the group together, others pulled it apart. The lesson was not only about biology, it was about who could live beside whom for a lifetime. Both numbers point at the same quiet truth. A self-sustaining colony is not a crew. A crew rotates. A crew has an end date and a ride home. A colony has neither. Its people are meant to stay until they die. A place where people stay until they die is a place where people are born. This is the turn the science keeps arriving at. The Mars-born child is not first a scientific choice. It is a demographic consequence. Wherever humans have settled for good, children have followed. There is little reason to expect Mars to be different. The child does not appear because someone runs an experiment. The child appears because someone builds a home and lives inside it. That distinction changes everything the measurements meant. Consider again the bodies we have studied. Scott Kelly spent 340 days in orbit and then came home. His arteries had thickened. His gene activity had shifted. Most of those changes reversed within months of landing. The reversal was the point. His body knew the way back, because it had first been built on Earth. The same is true of every astronaut in every dataset. The bone loss models describe skeletons that will return to weight. The fainting failures describe hearts that will relearn to stand. The extra height fades once the spine is compressed again. In each case, recovery is written into the result. The body is a traveller returning to a country it already knows. The Mars-born child has no such country. There is no baseline to recover. There is no earlier, heavier body waiting underneath the lighter one. The skeleton would be assembled under a weaker pull from the very beginning. The heart would learn its rhythm against that lesser weight. The balance organs would calibrate to a gravity a third of ours. Nothing about this child would be a departure from a norm. For this child, Mars is the norm. So the question inverts one final time. We have spent decades asking what space does to a human body. We assumed the danger lay in leaving Earth. For a Mars-born child, the danger would be arriving. Picture what arriving might mean. On Earth, an astronaut returning after months in orbit is often unable to stand. After long stays aboard the Russian station Mir, 5 of 6 astronauts tested could not finish a 10-minute upright tilt test on landing day. Their hearts could not hold blood pressure against the sudden pull. Those were trained adults who had lived their whole lives at full weight. They recovered because their bodies remembered the load. A child who had never felt that load would arrive with a heart that had never once pushed against it. The muscles would be thinner, the bones would be lighter. The simple act of standing might be the first crisis. Popular imagination reached this conclusion before the laboratories did. In 2017, a film called The Space Between Us told the story of a boy named Gardner Elliott. He is the first human born on Mars. He grows up in Martian gravity, tall and thin, tended by machines and a small crew. When he longs to see Earth, he is warned that his body may not survive it. His heart, he is told, is not strong enough for a heavier world. His bones were never built for it. The film is fiction. It is not evidence, and it should not be mistaken for any. No boy named Gardner exists. No child has been born on Mars or anywhere beyond Earth. Yet the story matters as a mirror. It shows that the question is not confined to journals and radiation counters. It has already entered the culture as a kind of rehearsal. Long before the first Martian pregnancy, we are imagining the first Martian who cannot come home. If the answer is truly unknown, the next question is whether it can be changed. Could anything let a Mars-born body cross safely to Earth? There are, at least, directions to look. The first is artificial gravity. A large habitat could spin. Spin creates a force that pushes outward, and to a body inside, that force feels like weight. In principle, a rotating settlement or a rotating nursery could raise the effective gravity a child grows up in. A child developed near Earth weight might keep a body prepared for Earth, but no such structure has ever been built at that scale. We do not know how fast it must turn, or how a growing child would tolerate the spinning itself. The second is medicine. Astronauts already fight bone and muscle loss with hours of daily exercise, with resistance machines, with careful drugs. A Mars colony might extend those countermeasures from adults to children. It might invent new ones we cannot yet name. But every countermeasure we have was designed to preserve a body that Earth already built. None was designed to build that body from the start. Slowing a loss is not the same as preventing an absence. The third direction is the longest and the strangest. It is adaptation across generations. Perhaps the first Mars-born children could never safely return. Perhaps their descendants, shaped over many lifetimes, would become something the word human strains to hold. A body tuned to Mars might one day be a Martian body in full. That is not a rescue. It is a divergence. It answers the question by letting the two worlds drift apart until the crossing no longer matters. Each of these paths is speculation stacked on speculation. None has been tested. None can be tested without the very child the whole question is about. To move beyond speculation, we would need a kind of research that has never been done. We would need to know what a body does when it develops in partial gravity over years, not days. Every dataset we have comes from microgravity, the near weightlessness of orbit, or from Earth itself. Mars sits between those two extremes. Its pull is real, but reduced. Almost nothing in our records describes what growth looks like in that middle band. This is why careful scientists refuse to give a firm answer. One reference written for future settlers puts it plainly. It states that no one currently knows whether a Mars-born child could adapt to Earth gravity later in life. It calls the problem unresolved. It even sketches how wide the uncertainty runs. At one end, the difficulty might be trivial, corrected with therapy and time. At the other end, it might be an obstacle no medicine can overcome. Both ends remain on the table. That is the true measure of our ignorance. The uncertainty is not a failure of effort. It is a consequence of where the data can and cannot come from. We can fly rodents and watch their newborns struggle. We can grow jellyfish and count the ones that pulse wrong. We can measure a twin's arteries and a rover's daily dose of radiation. What we cannot do is watch a human being grow from a single cell to a standing child under the gravity of another world. The one experiment that would settle the question is the one experiment we are least able to run. So the answer stays suspended. It hangs between the models and the missing measurement. It will hang there until someone, somewhere, either builds the spinning habitat that changes the terms, or simply lets a child be born beneath the thin sky of Mars and waits to learn what that child becomes. Whichever comes first, the body at the center of the question will not be asked. It will only be observed. It will grow according to the world it is given. It will learn the weight of Mars as the only weight there is, and that is why the smaller colony number carries a hidden condition. 22 people could hold together only with a supply ship every 2 years. True independence, the kind that needs nothing from Earth, asks for far more. Until a settlement reaches it, every Martian birth remains tethered to a planet the child has never seen. The distance between those two numbers is the distance between survival and permanence. 110 people can work a settlement. They can grow food and repair machines and keep each other alive. But a working settlement is not the same as a lasting one. A lasting one has to replace the people it loses. It has to raise the next generation itself. And that is the moment the whole question stops being about engineering. It becomes a question about a child. Konrad Schochik understood this early. He is a bioethicist, and beginning around 2018 he and his colleagues started writing about what reproduction on Mars would actually mean. Their conclusion was uncomfortable. They argued that a child born into such a place would in effect be the subject of an experiment. No one could ask that child for consent. No one could promise the experiment would be gentle. The child would arrive into a body whose development had no precedent and no control group. Every measurement taken of that body would also be the first measurement of its kind. The ethics did not stop at consent. Schochik and his colleagues pushed into harder ground. They asked what the value of a human life would be in a place so hostile to it. They asked how a small and isolated colony would decide questions of pregnancy and its ending, far from any court or clinic on Earth. And they raised a possibility that many people find difficult to hear. They asked whether it might be justified to genetically engineer children for Mars survival, not for vanity, for endurance. To give a body a better chance against radiation, against low gravity, against the slow erosion of bone. That idea turns the question inside out. Until now, the worry has been that a Mars child could not return to Earth. The engineering answer proposes something stranger. It proposes designing a child who was never meant to. A body optimized for 38% of Earth's gravity would be a body optimized away from the world its parents came from. The tether to Earth would not just be cut by distance, it would be cut by biology, deliberately, before the child ever drew breath. No one has done this. No one has seriously proposed doing it soon, but the fact that a bioethicist felt the need to argue about it tells you how real the underlying problem has become. And the problem begins before birth. It begins with whether a pregnancy on Mars could proceed normally at all. Here the evidence is thin, but it is not silent. Scientists have flown pregnant rodents in space, and they have raised others under simulated low gravity on the ground. The results point the same direction. Fetal weight lagged behind Earth controls. Skeletal development was delayed. The placenta itself developed more slowly, and the placenta is the organ that feeds and protects everything the fetus becomes. Labor ran long. And in the first week after birth, more of the newborn animals died than in the Earth groups. None of that proves a human pregnancy would fail on Mars. Rodents are not people, and simulated microgravity is not the real thing. But every one of those findings is a warning about a different stage of the same fragile process. If the placenta forms slowly, the fetus is underfed at the moment it needs the most. If the skeleton lags, the child that emerges may be built on a weaker frame from the start. And the first week after birth is already the most dangerous week of any mammal's life. Adding an untested gravity to it is not a small variable, it is the whole environment. Radiation makes the beginning even more uncertain. The dose that already threatens an adult astronaut's career does not spare the cells that make the next generation. In animal studies, radiation exposure has been linked to more breaks and damage in the DNA carried by sperm. It has been tied to a faster loss of the follicles in the ovary, the finite store of potential eggs a body is born with. A woman does not make new ones. Whatever radiation destroys is simply gone. So the Martian environment does not only threaten the child who is born, it threatens the possibility of conceiving a healthy child in the first place. The damage can arrive one generation early, written into the cells before those cells ever meet. This is the weight behind a premise that popular culture has already imagined. In the 2017 film The Space Between Us, a boy named Gardner Elliott is the first human born on Mars. He grows up in Martian gravity, and he is told plainly that his heart and his bone density are not equipped to handle life on Earth. The film is fiction. It invents its answer for the sake of a story. But it did not invent the question. It simply dramatized what real physiology already suggests. A heart that never learned to push blood against a full gravity. A skeleton that never carried a full weight. Both grown to fit a lighter world, and both facing a heavier one on the day they are asked to leave. So the honest state of the science is not a verdict. It is a range. The people who study this most carefully do not agree on how severe the problem is. Some frame it as a difficulty that medicine and engineering could eventually manage. Others treat it as a barrier that may never come down. The reference writing on Mars-born children says this openly. It admits that nobody currently knows whether such a child could ever adapt to Earth gravity later in life. It places the possibilities across an enormous span. At one end, the whole worry could turn out to be trivial, a body that stiffens and recovers the way returning astronauts do. At the other end, it could be an unsurmountable obstacle, a body so shaped by its first world that the second one is closed to it forever. Between those two ends lies almost everything that matters, and none of it has been measured. The reason for that ignorance is simple, and it is not laziness. The experiment cannot be run on Earth. Gravity here comes in exactly one strength. You cannot dial it down to 38% and hold it there for the 18 years it takes to raise a person. There is no facility anywhere that can grow a mammal from conception to adulthood under a steady fraction of Earth's pull. The nearest data we have are the jellyfish that developed their gravity-sensing crystals in orbit, and the rodent pregnancies cut short after days, not years. Both are proxies. Both hint. Neither answers. The one measurement that would settle the question requires the very thing whose safety is in doubt, which is a developing body actually living under low gravity for a lifetime. There is one path that could change the terms entirely. It is the spinning habitat. If a settlement could build a structure that rotates, it could manufacture its own gravity through centrifugal force, spin it fast enough, size it correctly, and the floor pushes back the way the ground on Earth pushes back. A fetus grown inside such a place would develop against a familiar pull. The inner ear would calibrate its otolith organs, its utricle and its saccule, to something close to Earth's gravitational vector rather than to Mars. The bones would load. The heart would work. In principle, a child raised in a full artificial gravity might grow a body that Earth would not reject. But that principle is not yet a plan. No such habitat exists on or near Mars. Building one large enough to spin gently and comfortably is an engineering task of a scale no settlement has attempted, and it would have to be reliable across a childhood, not a demonstration. A spinning home that fails is not a nuisance. It is a sudden return to Martian gravity for a body in the middle of forming. So the artificial gravity answer is real, but it is a promise rather than a fact. It describes a Mars where the question never has to be asked, because no child is ever left in low gravity long enough to be shaped by it. We do not live in that Mars yet. We may never build it, which returns the whole problem to the body itself, and to the single hardest measurement of all: the return trip. A child raised in 38% of Earth's gravity would have spent every day of life under a lighter load than any human ancestor ever knew. The bones would have grown to match it. The heart would have sized itself to it. The balance system would have learned Mars as the definition of down. And then, on the day that child stepped toward a ship bound for Earth, the destination would be a world nearly 3 times heavier than the one that built them. For an adult astronaut, that transition is already brutal, and it is temporary. Their bodies were made on Earth and are only borrowing the difficulty. Roughly a third of returning shuttle crews could not hold their blood pressure standing up on landing day. After long stays on the old Mir station, 5 of 6 astronauts tested could not finish 10 minutes upright on the tilt table. Those were bodies coming home to a gravity they were born into. A Mars child would not be coming home. They would be arriving, for the first time, into a gravity their body had never once experienced and had never been designed to survive. Nobody can say, from any data we hold, whether that arrival would be an ordeal they recover from or a threshold they cannot cross. The models can describe the loss. They cannot describe the child. There is one organ that turns this worry into something firmer than speculation. It sits deep inside the inner ear, and it is very small. Two tiny chambers there are called the utricle and the saccule. Inside them rest crystals of calcium. These crystals are heavier than the fluid around them. When the head tilts, gravity drags the crystals sideways. That drag bends a bed of fine hairs beneath them. The bent hairs send a signal, and the brain reads it as down. This is the otolith organ. It is the body's private plumb line. It does not learn balance from instruction. It learns balance from gravity itself. Here is the detail that matters for a Mars child. The vestibular system forms early in fetal life. It begins assembling while the rest of the body is still being built. And it does not simply switch on, it calibrates. It tunes itself to whatever pull the growing body actually feels. On Earth, that pull never changes. Every fetus that has ever existed grew inside the same steady downward force. The inner ear of every living human was tuned to one gravity, the gravity of this planet. A child conceived and grown on Mars would be the first exception in the entire human story. Their otolith organs would calibrate to a lighter world. Their sense of down would be a Martian sense of down, learned before their eyes ever opened. Balance itself would be built to the wrong planet. We are not entirely blind here. The most useful evidence comes from an unlikely animal. In 1991, a space shuttle mission carried an experiment that now reads almost like a warning. On board were 2,478 polyps of the moon jellyfish. A polyp is the small anchored early stage of a jellyfish life. In 9 days of weightlessness, those polyps did what they do on Earth. They budded and multiplied. They produced nearly 60,000 young jellyfish, the free swimming stage called ephyrae. A jellyfish belongs in this story because of how it senses gravity. It has no brain and no inner ear, but it does have graviceptors, small structures that tell it which way is up. Those structures work with crystals of calcium. It is the same basic trick the human inner ear uses. A jellyfish and a person are separated by hundreds of millions of years, yet both reach for calcium and gravity to answer the same quiet question. So the experiment was really a test of that question. Grow a gravity-sensing creature without gravity, and watch what its sensors become. The result was plain. The jellyfish raised in space did not swim normally. When they were later observed, a striking share moved wrongly. Roughly 18.3% of the space-grown ephyrae showed abnormal pulsing and swimming. Among the jellyfish raised on Earth, that same defect appeared in only 2.9%. The animal's built-in weightlessness struggled to tell their own bodies how to move. No one should stretch a jellyfish into a human. A pulsing bell is not a walking child. But the principle underneath is not tied to any one species. A gravity sensor that grows in the wrong gravity may simply grow wrong. It may set itself to a world it will not have to live in. For a Mars child arriving on Earth, that would not be a swimming defect. It would be a sense of balance calibrated to a planet nearly 3 times lighter, suddenly asked to hold a body upright in full Earth weight. And balance is only the part of the problem we can watch. The deeper unknown sits earlier, before birth, before even conception. We do not know whether a human pregnancy could proceed normally on Mars. It has never been attempted, and the animal data we do hold is unsettling. Pregnant rodents have been flown in space and raised under conditions that mimic reduced gravity. Their pregnancies did not simply copy Earth. Fetal weight lagged behind. Skeletal development was delayed. The placenta, the organ that feeds a developing body, formed more slowly than it should. Labor ran longer, and in the first week after birth, more of the newborn animals died than among the Earth-raised controls. The trouble begins even before a pregnancy exists. Reproduction starts with cells that must move and meet. In simulated weightlessness, sperm lose their way. Studies show impaired motility and disoriented swimming. Cells that no longer travel in a clean line toward their target. There is hormonal disruption layered on top of that. Then radiation enters the picture. The same radiation Mars pours onto its surface every single day. In animal models, that exposure is linked to increased DNA fragmentation in sperm. It is also linked to an accelerated loss of the follicles that hold a female body's future eggs. Each of these is a crack in a chain that must hold perfectly for a healthy child to begin at all. Stack these unknowns together, and a sober picture appears. We cannot yet say whether conception would succeed. We cannot say whether a pregnancy would reach full term. We cannot say whether a body grown in 38% gravity would build a normal skeleton, a normal heart, a normal inner ear. Each of these questions casts an animal shadow, and every shadow points toward difficulty. None of them has a human answer. The honest position is not confidence in either direction. It is that the experiment would be run on the child themselves. This is where the science quietly hands the problem to ethics. A bioethicist named Konrad Sochik and his colleagues have spent years writing about exactly this future. Their conclusion is not comfortable. A child born on Mars, they argue, would in effect become the subject of an experiment they never agreed to join. The child does not choose the gravity. The child does not choose the radiation. The child does not choose to be the first real test of whether a human can be built on another world and still survive it. Their work raises questions that have no settled answer anywhere on Earth. What is the value of a human life placed deliberately into a hostile environment? What becomes of consent inside a sealed colony where simply leaving is not an option? What would a small settlement do about a pregnancy that turns dangerous, far from any hospital that could help? And there is a harder question underneath all of them. If survival on Mars demanded changing the child before birth, editing the instructions that build a body, would that be protection? Or would that be a new kind of harm? These are not questions an engineer can answer with a better spacecraft. And before any of this becomes real, there is a planar barrier, a matter of simple arithmetic. A first Mars child is not born to a lone explorer standing on empty ground. They are born into a settlement large enough to sustain itself. How large that must be is genuinely unsettled. One study, published in 2020, calculated a minimum of 110 people to keep a Mars colony working and alive. A later simulation, testing how different personalities endure isolation, argued the figure might fall as low as 22, provided the settlement was resupplied from Earth every 2 years. Somewhere between those two numbers lies the moment when a Mars-born child stops being a thought experiment and becomes a person with a name and a birthday. That gap in the numbers is not a small detail. It is the difference between a mission and a civilization. 110 people is a village that must grow its own food, mend its own machines, and raise its own next generation without a lifeline. 22 is a crew that leans on Earth for survival and gambles that resupply never fails. In either case, the child at the center of this story is not planned like a mission objective. They arrive because people are people, and people, given enough time and enough shelter, tend to build families wherever they manage to live. So the pieces of the problem all point inward toward the same body. A skeleton modeled to lose a third of its strength on the longest journeys. Muscles that waste without constant effort. A heart trained by a lighter world. An inner ear tuned to a Martian down. And a beginning, the pregnancy itself, that no human has ever tested off this planet. None of these facts, taken alone, closes the door, but together they describe a body shaped by Mars from its first cell, and quietly unfit for the planet its parents left behind. And so the question changes its shape. It stops being only a matter of bone and blood. It becomes a matter of consent. A child cannot agree to be born. That is true on Earth as well. But on Earth, a newborn inherits a world its species has already survived for a very long time. A child born on Mars inherits something no human body has been proven to endure. Its skeleton, its heart, its inner ear, and its earliest cells all begin their work inside a gravity no infant has ever known. The bioethicist Konrad Sochik has spent years turning this exact discomfort into a formal argument. He and his colleagues describe the first Mars child in plain and unsettling terms. Such a child, they write, would effectively be the subject of an experiment. Not a patient, not a settler, a subject. That word carries weight in science. An experiment implies an unknown outcome. It implies risk accepted in advance. On Earth, we surround human experiments with rules. We require informed consent. We require the freedom to refuse. A newborn can do neither. So the first pregnancy on Mars would place a helpless body at the center of a test whose result nobody can predict. The parents could consent for themselves. They could not truly consent for the child, and the colony around them could not undo the outcome once the child drew its first breath. Sosik pushes the discomfort further, into places most mission plans avoid. He asks what the value of a single human life becomes in a settlement where every resource is finite. He asks how a small, isolated community would handle a pregnancy that goes badly wrong. On Earth, a dangerous pregnancy meets a hospital. On Mars, it meets a few people, limited medicine, and no way home for many months. He asks whether abortion policy in such a colony could resemble anything we currently recognize. And he raises the hardest question of all. If a Mars-born body cannot thrive under Martian conditions, would it ever be acceptable to engineer future children to fit the planet? To edit the human template so that a child is built for Mars from its first cell? These are not abstract puzzles. They sit on top of a biology we barely understand. Because before a Mars child can be born, a Mars pregnancy has to begin, and the earliest steps of that process already look fragile beyond Earth. In studies of reproduction under microgravity and simulated microgravity, sperm lose their sense of direction. They swim in disoriented paths rather than clean ones. Their motility falls. The cells that carry half of a new human's blueprint behave as if they no longer know which way to go. Hormonal signals that normally guide reproduction show disruption in the same research. The machinery of conception, so reliable here, grows uncertain the moment gravity is removed. Radiation adds a second, quieter threat to that same machinery. In animal models, radiation exposure has been linked to increased sperm DNA fragmentation. The genetic instructions inside each cell arrive damaged. In females, the same kind of exposure has been linked to accelerated loss of ovarian follicles. The finite store of eggs a body carries dwindles faster than it should. None of this proves conception on Mars is impossible. But every one of these findings is a warning flag planted early, long before a fetus exists at all, and a pregnancy on Mars would unfold inside a bath of radiation that never fully stops. The surface dose Curiosity measured is not dramatic in any single hour. It is dangerous because it never pauses. A human fetus develops for roughly 9 months. Every one of those days would add to a total dose gathering in the smallest and most vulnerable cells a person ever has. On Earth, the womb sits shielded beneath a thick atmosphere and a strong magnetic field. On Mars, neither shield exists in the same strength. The developing body would grow inside the very environment that already pushes an adult astronaut toward the exposure limits agencies set for an entire career. The closest thing we have to real data comes not from humans, but from animals. Pregnant rodents have been carried into space and studied through their pregnancies. Others have been raised in conditions that simulate a weaker pull. The results are consistent and sobering. Their unborn young gained weight more slowly. Their skeletons developed on a delay. The placenta, the organ that feeds a growing fetus, formed more slowly as well. Labor itself ran longer than it should, and in the first week after birth, more of the newborns died than in the Earth-based control groups. These are not human results. A mouse is not a person. But they are the only windows we have into how mammalian development responds when gravity changes. And every window shows strain. Consider what growth itself would mean in this setting. An adult who spends months in orbit can grow up to 3% taller. The spine lengthens as its discs expand without gravity pressing down. For a 6-foot adult, that can mean close to 2 inches of extra height. The change is striking. But it reverses. Within months of coming home, the spine settles back under Earth's weight. That reversal matters, because it tells us the adult skeleton is only being stretched, not rebuilt. A child is different. A child's skeleton is not finished. It is still forming, still laying down its final shape year after year. Nobody knows what a lighter gravity would do to a skeleton that has never known anything heavier. The stretching that reverses in an adult might, in a child, simply become the shape, and we have no measurement that tells us otherwise. Picture the moment itself, stripped of all the models and all the numbers. A first cry inside a sealed habitat. A small crowd of settlers gathered where no crowd has gathered before. It would be one of the most significant births in the history of our species. It would also be one of the most uncertain. Every adult in that room would have arrived from Earth carrying a body built by Earth. The infant among them would be the first human being whose body was assembled entirely somewhere else. From the first division of a single cell, that child would be a native of a world with roughly a third of our gravity. Not a visitor, not a returning traveller, a native. So the picture assembling itself is not a single catastrophe. It is a sequence of unknowns stacked one upon another. Conception may prove harder than on Earth. Gestation may run slower and more dangerous. The radiation never rests. The growing skeleton may set itself to a lighter standard, and even if a healthy child is born, even if every one of these hazards is somehow survived, the deepest question still waits, untouched by all of it. Not whether the child can be born on Mars. Children in the end will be born wherever people live long enough to raise them. The question is what happens afterward, whether that child, grown strong for one world, could ever safely stand on the world its parents came from. That is where the science grows quietest and most honest. Because for every measurement we have gathered from adults returning to Earth, we have nothing at all from a body built the other way. We know what a lighter gravity does when it is taken away from a mature skeleton. We do not know what it does when it is the only gravity a skeleton ever had. Consider what that absence really means. Every projection in this field is an argument by analogy. We take a body shaped by Earth, remove some of its gravity for a measured span, and record what breaks. Then we reason backward toward a body that was never shaped by Earth at all. The logic runs the wrong direction. A skeleton that thins after decades of full weight is not the same as a skeleton that was laid down light from the very first cell. One is a subtraction, the other is a foundation. And no experiment yet performed has touched the foundation. This is why the animal record matters more here than anywhere else. When investigators flew pregnant rodents in orbit, and when they raised others under simulated low gravity, the offspring did not simply arrive smaller. Their skeletons developed on a delay. Their fetal weight lagged behind Earth-raised controls. The placenta itself formed more slowly, as though the organ that feeds a pregnancy could sense the missing pull. Labour ran long, and in the first week after birth, more of the newborns died. These are not human numbers. They are warnings written in another species. But they are the closest thing we have to watching development happen in the wrong gravity, and every signal points the same way. The trouble reaches back even further than pregnancy. It begins before conception. In microgravity and its ground-based simulations, sperm lose their sense of direction. They swim, but they swim disoriented, unable to hold a straight course toward the egg. Hormonal signaling drifts, and when radiation is added to the picture, the damage sharpens. Animal studies link the kind of exposure a Mars settlement would live inside to increased fragmentation of sperm DNA, and to an accelerated loss of the ovarian follicles that hold a lifetime supply of eggs. So the question is not only whether a fetus can grow correctly in 38% of Earth's gravity, it is whether two adults, already carrying the wear of the journey, could reliably begin a pregnancy at all. Stack these unknowns, and a strange picture forms. Conception uncertain. Gestation slowed and endangered. A skeleton built to a lighter standard. A nervous system tuned to a gravity that Earth does not offer. And through all of it, the steady dose from above never pausing, counted in the same units that already cap an adult astronaut's entire career. The child at the center of this is not a thought experiment for the people who would raise it. It is a life. And that is where the science hands the question to a different discipline entirely. A small group of bioethicists has begun to take that handoff seriously. The philosopher Konrad Socik and his colleagues have argued, in a series of academic papers, that the reproduction of humans on Mars raises problems no mission plan can engineer away. Their central discomfort is simple to state. A child born into that environment cannot consent to it. It cannot agree to grow up under radiation that an adult worker would be pulled from duty for absorbing. It cannot agree to a body that may never tolerate its parents' homeworld. Socik puts the matter plainly. Any such child would effectively be the subject of an experiment, not a metaphor for one. An actual experiment, run on a person who never volunteered. From there the questions multiply, and each one is harder than the last. What is the value of a human life in a place that is trying constantly to end it? Who decides whether a pregnancy on Mars should continue when there is no hospital to fall back on and no way home? If a settlement discovered that its children were failing to develop normally, what would it do, and who would hold the authority to choose? These are not questions astronomy can answer. They are older than astronomy. But Mars sharpens them, because Mars removes every institution we normally lean on. There is no wider society to appeal to. There is no next town with a better clinic. There is only the colony, and whatever it has already decided to become. The bioethics discussion pushes even into the body's blueprint itself. If a child cannot be made safe for Mars by medicine alone, some have asked whether it should be made safe by design, whether the genes of the next generation might be edited toward denser bone, or greater radiation tolerance, or a heart better matched to a lighter world. The scientists raising this do not endorse it. They raise it because it sits at the end of the same road. Once you accept that a natural human body may not survive being born on Mars, you are forced to ask how far you would go to change the body instead of the plan. And a body engineered for one planet may be a body engineered away from every other. The first Mars-born child could become, quite literally, a person built for a single address in the universe. All of this assumes there is a settlement large enough for children to even be a question. And here the numbers turn oddly small. For years, the popular imagination pictured thousands of colonists before anyone spoke of a first birth. The peer-reviewed estimates are more modest, and they disagree with each other sharply. One study, published in 2020 by the researcher Jean-Marc Salotti, worked through the labour and resources required to keep a colony alive without constant rescue from Earth. His minimum viable number came out to 110 people. Enough hands to grow food, maintain machines, treat the sick, and still have margin when something fails. A later analysis pushed the figure even lower, using an agent-based simulation, which models a colony as many individual people interacting rather than as a single average. Researchers suggested a settlement might hold together with as few as 22 people. But that number carries a heavy condition. It assumes the right mix of personalities, chosen to endure isolation without fracturing, and it assumes a resupply ship arriving from Earth roughly every 2 years. 22 people, carefully selected, quietly restocked. That is the smaller edge of the estimate. 110, self-reliant, is the more cautious one. Either way, the founding population of a permanent Mars is closer to a village than a city, and somewhere inside that village, if it lasts, the first pregnancy begins. It is worth pausing on how thin these founding numbers are, because they change the meaning of every risk already named. On Earth, a rare developmental problem is rare precisely because there are billions of us. In a settlement of 22, or even 110, there is no statistical cushion. A single failed pregnancy is not a data point. It is a substantial fraction of the colony's future. A cluster of children with skeletons too light for Earth is not an anomaly to be studied later. It is the next generation. The smallness that makes a colony possible is the same smallness that makes its mistakes irreversible. The culture around us has already rehearsed this future, long before the science could answer it. In a film released in 2017, A boy named Gardner Elliott is imagined as the first human born on Mars. He grows up in Martian gravity, curious about the world his mother came from, and when he finally reaches Earth, he is told the thing this whole question circles, that his heart and his bone density were never built for this place, that the pull he is standing in is too strong for a body assembled somewhere lighter. The film is fiction. Its physiology is dramatized, not measured, but it is a real articulation of a real fear, and it reached far more people than any journal paper ever will. It gave the anxiety a face before the laboratories could give it a number, and the laboratories, so far, have not given a number. This is the honest heart of the matter, and it deserves to be stated without decoration. When you ask the people who study this whether a Mars-born child could one day adapt to Earth, the careful answer is that nobody knows. Not the physicists, not the physicians, not the ethicists. Written summaries of the problem place it across an enormous range. At one end, it may turn out to be a trivial difficulty, something a few months of therapy and training could correct. At the other end, it may prove an insurmountable obstacle, a body so shaped by low gravity that full weight would injure it beyond recovery. Between those two extremes lies almost the entire truth we currently possess. Not a finding, a width of uncertainty. Closing that width will require the one thing no agency has yet built, a place to study development in partial gravity over a long time, using living bodies across whole life stages, not just the days a shuttle can carry. We have measured what happens to grown astronauts who leave gravity and return. We have flown jellyfish and raised rodents and modelled bone loss out to the far edge of a mission. What we have never done is watch a mammal conceived and grown and matured under a steady, gentle, unrelenting fraction of Earth's pull, and then asked it to come home. Until that experiment exists, every confident sentence about the first child on Mars is running ahead of its evidence. The most scientific thing we can say is also the least satisfying. The measurement has not been taken, the body has not been built, and the return trip, the passage from 38% of gravity to the full weight of the world its parents left, remains the one journey no one has ever tested on a traveller who began their life out there. So the question does not end with the body. It moves to the machines and the medicines we might build around it. If low gravity is the danger, then the obvious answer is to manufacture more of it. Engineers have long proposed spinning a habitat so that its rotation presses the occupants outward. A large enough wheel, turning at the right rate, could push a body against its floor with something close to the weight of home. In theory, a Mars settlement could hold a spinning chamber where a pregnancy unfolds under a heavier engineered pull. It is a clean idea on paper. It has never been built at that scale. It has never held a growing human for a single day. Even if such a chamber existed, no one knows what dose of gravity a developing body actually needs. A grown astronaut can borrow full weight for a few hours on a treadmill and still lose bone. The exercise countermeasures aboard the space station slow the damage but do not stop it. Calf muscle still shrinks by roughly 7% even under the heaviest training loads. So a spinning room is not a guarantee. It is a hypothesis about a threshold no experiment has yet located. We do not know how many hours of imitation weight a fetus would require. We do not know whether a few hours a day is enough, or whether only a constant pull will serve. Medicine offers a second set of hopes, and the same silence follows each one. Drugs already exist that slow bone loss in older patients on Earth. They were designed for aging skeletons. They were not designed for skeletons being assembled for the first time in a world that pulls with only 38% of Earth's force. Giving such a drug to a pregnant settler or to a Martian child would be a decision made with almost no data. The countermeasures we trust were all tested on adults who grew up under full gravity and then left it. A body built in low gravity from conception is a different subject entirely. It has never sat in any trial. This is where the science runs into a wall that is not made of physics. It is made of people, and of numbers far smaller than a planet. Before any child can be born on Mars, A community has to exist that could plausibly raise one. That community does not appear overnight. A study published in 2020 put a number on it. The researcher Jean-Marc Solotti estimated the minimum self-sustaining settlement at around 110 people. That figure accounts for the labor of survival. It accounts for the growing of food, the making of air and shelter, the effort of keeping a base alive without constant rescue from Earth. Other researchers have argued the number could be smaller. A more recent simulation took a different approach. It modeled how different personality types cope with isolation and stress. It suggested a founding group of as few as 22 people might endure. That lower estimate carries a heavy condition. It assumes regular resupply from Earth every 2 years. It assumes a lifeline still stretched across the dark. So the honest range runs from about 24 dependent settlers to more than 100 self-reliant ones. Somewhere inside that range, a first pregnancy becomes not just biologically possible, but socially thinkable. And the moment it does, the questions stop being about bone and blood. They become about consent. A child cannot agree to be born. No child ever has. On Earth, that fact is softened by the ordinary safety of the ground beneath them. On Mars, it is not softened at all. The bioethicist Konrad Sawczyk and his colleagues have spent years mapping this terrain, and their conclusions are uncomfortable by design. They point out that any child born on Mars would, in effect, be the subject of an experiment. No one could promise that child a healthy heart. No one could guarantee a spine able to bear Earth. No one could offer a balance system tuned to a world it could safely reach. The first Martian child would be a living test of hypotheses its parents could not answer. The ethics do not stop at birth. Sawczyk and others raise questions most people never have to consider. What happens if a pregnancy on Mars goes wrong, far from any hospital Earth could offer? What abortion policy governs a settlement of a few dozen people, where every decision touches the whole colony's future, whether it would ever be justified to edit the genes of an unborn child so it could better survive radiation and low gravity? These are not questions with tidy answers. They are questions about what we are willing to do to a person who cannot yet speak, in a place that will not forgive our mistakes. And this is the strange gravity of the whole subject. It is not only about a child who might not be able to visit Earth. It is about whether we should make that child at all, knowing what we do not know. The value of a human life does not change with distance from the sun, but the weight of the choice does. On Earth, a difficult pregnancy has centuries of medicine behind it. On Mars, the first pregnancy would have almost nothing behind it but hope, and a spinning room that may or may not work. It is worth remembering how uncertain all of this remains, because certainty is the one thing this topic cannot honestly offer. The clearest summaries of the question refuse to pretend otherwise. Even the plain-spoken entries written by the Mars settlement community itself say so directly. They state that no one currently knows whether a Mars-born child could adapt to Earth gravity later in life. The problem is described as unresolved, and its seriousness is left open. It might turn out to be a trivial problem, corrected by exercise and time. It might turn out to be an insurmountable obstacle, a wall no medicine can climb. Both possibilities are still on the table, because the research that would settle them has not been done. That honesty matters, because the culture around us tends to answer the question before the science can. The idea has already been dramatized. A film released in 2017 imagined exactly this premise. Its story follows a boy, the first human born on Mars, who grows up in Martian gravity. He is told that his heart and his bone density are not equipped for life on Earth. The film is fiction. It is not evidence, and it should not be mistaken for it. But it is a faithful mirror of the real anxiety underneath. It shows how naturally the human mind reaches for the tragic version of this story. A child born on one world, longing for another, told that his own body is the border he cannot cross. The science is more careful than the story, and less conclusive. It does not know that the Martian child would be trapped. It knows only that we have never grown a body in that pool and asked it to return. Everything between those two statements is projection. The bone models, the radiation counts, the jellyfish that could not tell up from down, the twins whose blood vessels drifted apart over a single year. Each is a real measurement. None of them is a child. They are the closest evidence we have. They all point in the same uneasy direction. But none of them completes the sentence the title begins. So we hold a set of true facts that do not yet add up to a verdict. We know that grown bodies lose bone in space, on a long Mars mission that loss could push past the edge of osteoporosis. We know that muscle wastes, that hearts forget how to fight gravity, that people who spend months aloft cannot always stand up on the day they land. We know that a gravity-sensing organ in the inner ear calibrates itself early. We know that creatures grown without a clear sense of down develop wrong. We know that radiation on Mars would, over one mission, meet the cancer risk limits set for an entire adult career. Each fact is solid. Each was earned by careful people watching careful instruments. What we do not know is how these facts change when the body in question never knew Earth at all. Adaptation cuts both ways, and we understand only one edge of it. An adult who leaves gravity is losing something they already had. A child grown in low gravity would never have had it. That child might build a body perfectly suited to Mars, and perfectly unsuited to the world of its ancestors. That is not a tragedy the data has proven. It is a possibility the data cannot yet rule out. The distance between those two ideas is the entire open question, and it is where the search must go next. The search has a shape, even without an answer. It begins with the honest admission that we are reasoning from the wrong bodies. Every measurement we trust came from an adult who was born on Earth. Scott Kelly grew his bones under full gravity for decades before he ever floated above it. His 340 days aloft changed him, and then most of those changes faded. Roughly 91% of his altered genes returned to their old settings within 6 months. That recovery is the quiet hero of the whole story. It is also the part we cannot promise a Mars-born child. Recovery assumes there is an original state to return to. A body built in 38% gravity has no such baseline. It is only the world it was made for. So the confident statements are narrow, and they are worth stating plainly. We know that weight-bearing bone thins by roughly 1 to 1.5% each month without gravity to load it. We know that muscle wastes. We know that the heart forgets how to fight a standing column of blood. We know that the spine stretches and then settles again on return. We know that the inner ear tunes its sense of down to whatever pull surrounds it early in life. We know that moon jellyfish grown in orbit developed their gravity sensors wrong, with abnormal movement in nearly 1 in 5. We know that the radiation crossing to Mars and resting on its surface would spend an adult's entire career dose in a single round trip. These are not guesses. They are instruments and careful people, repeated and checked. What we do not know is what happens when all of these forces act not on a visitor, but on a beginning. A child on Mars would not lose bone density. It would simply never make as much. It would not lose muscle mass on a voyage. It would build a frame calibrated to a lighter world. Its balance would not drift toward Mars. Its balance would be Martian from the first heartbeat that could sense direction. And the return trip we keep circling would not be a homecoming. It would be an arrival on a heavier planet the body had never met. Earth would press down with more than 2.5 times the weight that child had ever carried. The spine would compress, the heart would strain, the legs might not hold on landing day, the way 5 of 6 long-duration astronauts once could not hold themselves upright. This is why the premise refuses to become simple fiction. The film that dramatized it imagined a boy whose heart and bones could not survive the planet of his ancestors. The film is invented. The physiology it borrowed is not. The bioethicists who study this problem do not argue about spacecraft. They argue about consent. A child cannot agree to be born into an experiment whose result is its own body. If that body turns out to be unfit for Earth, no one chose it, and no one can undo it. That is the heaviest sentence in the entire question. It carries no numbers at all. There is also the matter of how far away all of this remains. Before any child is born on Mars, there must be enough people to make such a birth ordinary rather than reckless. The estimates run from about 110 settlers down to as few as 22, and they assume steady supply from Earth. We are nowhere near either figure. No human has been conceived, carried, or born anywhere but this planet. The pregnant animals flown into orbit gave us warnings, not verdicts. They showed delayed growth, troubled births, and more deaths in the first fragile week. They did not show us a healthy child adapting to a lighter world and thriving there. We have never seen that. We have only seen the edges of the risk. So the strongest unresolved question is not whether a Mars colony can be built. It is whether a human life can begin in low gravity and remain free to move between worlds. Everything we have measured points at a single suspicion. Adaptation is not neutral. A body shaped by Mars would be exquisitely fit for Mars and quietly stranded by that fitness. Marspedia states the uncertainty without flinching. The problem might be trivial. It might be insurmountable. We do not yet possess the one thing that would settle it. We have never watched a mammal grow from conception to adulthood in partial gravity and then tested it against a stronger pull. Until that experiment exists, honestly and ethically, the answer stays open. It is a strange place for a science to rest. We can model bone loss to within a few percent. We can count the radiation falling on a rover's sensor. We can trace a single astronaut's genes back toward their origin. And yet the simplest question a settler might ask, whether their child could ever see the planet in their family stories, has no answer we are allowed to give. The measurements are precise. The conclusion is empty. That gap is not a failure of the instruments. It is the shape of a question no instrument has yet been permitted to ask. Perhaps artificial gravity will erase the problem before it arrives. A spinning habitat could give a growing child something close to Earth's pull, and the body might develop as it always has. Perhaps generations of slow adaptation would build people who belong to Mars and never long for anything else. Perhaps the first Mars-born child will step onto Earth one day, unsteady but unbroken, and prove every worry wrong. Each of these is possible. None of them is proven. They are futures, not findings. For now, the truth is smaller and colder and more human than any of them. Somewhere ahead, if we keep going, a child will draw a first breath under a rust-colored sky. That child will grow up light on its feet in a way no Earth child ever was. It will run and stumble and heal inside 38% of the gravity that shaped all of human history, and the pale point its parents call home may remain exactly that, a point. Visible, named, remembered, and gently out of reach. A world its body was never built to hold. We built the science to carry us outward. We are only beginning to learn what it might cost the ones who would be born once we arrive. The bones, the blood, the inner ear, the invisible dose, the unasked consent. They all gather around one small figure who does not exist yet. When that figure finally does, the answer will stop being a model and become a life. Until then, the safest thing we can say is also the quietest. A child of Mars would belong to Mars completely, and that belonging might be the one journey from which there is no return.